In this example, we're going to be calculating the maximum bending stress for a beam. Now, we have some more information about this beam. This example actually is very interesting in that it combines a lot of the topics in the course. It combines the shear and moment diagram components of the course that we just completed with things like moment of inertia, centroids, that kind of stuff. So this is a very interesting example. In this example, of course, we have a beam that's being loaded. We have reaction of 1,066.67 on the left. We have a 2,000 pound force here. We have a uniform load of 400 pounds per foot. Okay, we have reaction again here of 2533.33. And again, I went ahead and just calculated the reactions so that we can really focus more on the components of the shear and bending moment diagrams and the moment of inertia and so forth. Okay, now, in this particular case, what's unique about the problem is we know something about the beam. It is a nominal 4x12 timber. Okay, it's an S4S beam. If you go at the back of your book, you'll find tables with the different properties of beams. Now, we say 4x12. That's a nominal size. It's kind of like when you say, "Oh, I have a 2x4." Well, 2x4 really isn't 2 inches by 4 inches, and likewise, this 4x12 isn't really exactly a 4x12. Its width is 3.5 instead of 4, and its height is 1.25 instead of 12. But again, this is just a nominal size. Now, the approach that we're going to be using is to use this formula that was derived in the lesson, in which the bending stress is equal to the bending moment times c over the moment of inertia. And I'm going to kind of take you through each one of these calculations as we go. So let's go ahead and start with the moment of inertia piece. Okay. If we look up the moment of inertia for a rectangle about the centroid, recall that it was 1/12 the base times the height cubed. Okay. So if we substitute those values in, our base is 3.5 inches. Our height is 11.25, and that value would be cubed. We come up with a moment of inertia of 415.28 inches to the fourth. Okay. Now, for our c value, c is defined as the distance from the neutral axis, right, which deals with the centroid, to the outermost fiber of the cross section. Now, because this is symmetric, it's a rectangular section, right? The c distance here would be the same as the c distance here. And c is just going to basically be half of that distance. So it'd be half of the 11.25, which comes out to be 5.625 inches. Okay, so we know c, and we know the moment of inertia. So we've got two of these three terms. Okay, for us to calculate the bending stress, of course, we need bending moment. Now, we could do the bending moment anywhere, but in this problem, we specifically want to calculate what the maximum bending stress is. So we're gonna have to use the shear moment diagrams to figure out where we have the maximum bending moment, so that when we calculate the bending stress, we get the maximum bending stress. And I'm going to use the exact same approach that we did earlier in class, where in this case I'll have a girl as she's walking across the beam. Okay, we're not going to use the technique where we're making cuts. We're just going to use the technique based on the different relationships we know between the shear, the bending moment, and the loading areas. Okay, so as she walks across the beam, of course, she first encounters this reaction here of 1066.67. Okay, as she walks across the beam, again, there's no change in shear because there's no area under the loading curve. There's just point loads. Okay, until she gets to a distance of 4, in which she encounters a 2,000 pound force. Okay, so this would take her to a value of minus 933.33. Okay, walks across, again, she's not encountering any change in shear because there's no change in the loading, right? There's no loading area, so there's no change in shear. And then she gets to this reaction right here of 2533. Okay, this is going to take us up to a value of 1,600. I apologize, I'm kind of running a little tight on space here, but this will give us a shear value of 1,600. And then we have to try to figure out what's going on with shear from this point here over the 4 feet of distributed load. Now, it's a uniformly distributed load. And again, we know the shear varies as the difference in shear between 2 points is related to the area under the loading curve, right? So for every foot that we move over, we're going down 400. So when we move over 4 feet, we'll go down to 1,600. And again, it's going to be a linear relationship because for every foot we move over, it drops a constant 400 pounds, okay? Now, we can use this information to come up with the bending moment, okay? The first thing I'm going to look at is I'm trying to look at and see if I can figure out what these values are going to be. Remember, we need the areas underneath this. So if I take 1,066.67 and I multiply by 4 feet, this comes out to be 4266.7. Again, that would be the area. Okay. Now we have a distance here of 8, okay? And if I have 8 feet times 933, I have to look at my cheat sheet over here, that comes out to minus 7466.7 for this area. Okay. And then this one piece here, we have a triangle with a base of 4 feet, a height of 1,600. So 1/2 the base times the height comes up with an area, gives us an area of 3,200. So now we can use this information about the area under the shear, right, under the shear diagram from each point to figure out what the bending moment will be at each point. So again, this is 4266. It's a linear relationship as we talked about in the earlier video because for every foot we move over, we gain 1,066.67 of bending shear. So this is linear. It goes up to a value here of 4266.7. Okay. Then we drop down 3466.7. Again, this is a linear relationship because for each foot, that area, right, when you go over 1 foot, it's 7466.7. When you go over 2 feet, it's twice that and so forth. So it's a linear relationship. And go all the way down here. Okay. And if I take 4267 and I subtract 7466.7, I get a value here of minus 3,200. Okay. And then from 3,200, we have a positive area of 3,200. So we know it's going to close. The question is, what's the shape look like? To me, the easiest way to figure out what this shape is going to look like is I consider, for example, if I just looked at a 1 foot wide slice of this, and I see if I had a 1 foot slice here versus if I had, say, a 1 foot slice here, okay, again, if the slice width is the same, here, that 1 foot slice gives you a big change, a big area. Here, that 1 foot slice gives you a really minor area. So we see, basically, it's a second order equation where we see a lot of change at the very beginning and little change at the end. That's not the best of diagrams, but it is a second order curve, okay? Now what we're really after in this value, in this application, because to calculate the maximum bending stress, we need that maximum bending moment, okay? It could be a positive or a negative bending moment. In this case, we see we have to choose between either the 4266 or the 3,200. So this is definitely the larger of the values. And so all we have to do now is kind of plug and chug and calculate the bending stress. So we know that our maximum bending moment is 4266.7. The units on that are pound-feet. Oh, pound-feet, all right. Okay. Then we're going to be multiplying by C. Now C is in inches. I'm going to go ahead and convert everything here into inches. So in a foot, we have 12 inches. Okay, so that'll cancel here. So now we have pound inches. I'm going to be multiplying by inches, which is 5.625 inches, which is the C value. And then the denominator, we have this value here, the moment of inertia, 415.28 inches to the 4th. And so essentially what we have in the numerator is pound inches squared divided by inches to the 4th. Okay, that will give us a final value of 693.5 pounds per inch squared, right? Also known obviously as a PSI. Okay. And that's our maximum bending stress. So again, we had to kind of combine the content from various lessons for this example. We had to figure out what the moment of inertia would be based on the formula 1/12 bh cubed. We had to look at the cross-section, figure out what C would be based on the location of the neutral axis or the centroid. And then we had to look at the maximum bending moment, which we had to derive getting the shear stress first. So with that, that concludes our example.